So, in this lecture we will learn about Cantor set, construction of Cantor set, and its properties, whether Cantor set is closed or not, how to identify whether any given real number is member of Cantor set or not, suppose f denotes the Cantor set. Then again we will see that Cantor set is uncountable despite its length tending to 0. This set is nowhere dense, that is interior of the closure of Cantor set is empty. It is a perfect set and also has self similar repeated structure and is one of the basic example of fractal. So, this will do one by one. So, let me start with the construction of Cantor set. Here I is the closed interval 0 1 or say f naught, then f1 is found by basically removing the open middle third 1 by 3 to 2 by 3 from closed interval 0 1. So, suppose this one is f naught, let us divide into 3 equal parts, say 1 by 3 to 2 by 3 and remove the middle one, So, we will have this portion from 0 to 1 by 3 and from 2 by 3 to 1. The end points 1 by 3 and 2 by 3 are included in this f1. So, one can write f1 as closed interval 0 to 1 by 3 union 2 by 3 to 1. Now, we need to repeat this process infinitely. So, f2 is obtained again by removing the open middle third of each of the two closed intervals in f1, that is this one. So, let me divide this one. I can do it, say again we are going to divide it on into 3 equal parts. So, I can multiply its numerator and denominator by 3. So, this point 1 by 3 I can write it as 3 by 9 and this as 0. So, 1 by 9, 2 by 9 and 3 by 9. Let us remove this interval and similarly from this one say 2 by 3 and this one is 1. So, again we are going to divide since into 3 equal parts. So, I can write it as 9 by 9 and this 2 by 3 multiply this numerator and denominator by 3. So, this will be 6 by 9. So, the next point will be 7 by 9 into 3 equal parts and this will be 8 by 9. So, what we need to do? We need to remove the open middle third, that is from open 7 by 9 to 8 by 9 and here from open interval 1 by 9 to 2 by 9. So, the remaining part, these 4 parts will constitute this f2. So, f2 is from 0 to 1 by 9, and from 2 by 9 to 3 by 9, this portion from 2 by 9 to 3 by 9 and here from 2 by 3 to 7 by 9, and 8 by 9 to 1. So, we need to repeat this process infinitely to obtain f1, f2, f3 and so on. Now, what will be the Cantor set? Intersection of all these fi's, the same structure is shown here. After removing the open middle third, the remaining part, this one is f1. Here we again have 4 equal parts, intervals, closed intervals. This is f2, similarly f3 and f4 and so on. So, intersection of all these fn's where n is equal to 1 to infinity is basically the Cantor set. Intersection of all these closed intervals, union of closed intervals, say f1, f2 form f1 is union of the closed interval, not an interval. f2 has 4 equal parts mentioned here. So, this is what Cantor set. Now, next part is how to identify that whether any given real number is member of Cantor set or not. So, this can be very well explained using the ternary representation of a real number. So, if we recall the ternary representation of a real number, let us let me add here one page for the purpose of explanation. Yes. So, if we recall ternary representation of real numbers, in closed interval 0 1, For other real numbers, we can do translation. So, for example, in earlier lecture I have already explained it that on dividing this into equal intervals, say 1 by 3, 2 by 3. In ternary representation, we need to use the symbol 0, 1 or 2, 0, 1 and 2. Let us denote this interval from 0 to 1 by 3 by the notation 0, this by 1 and this by 2. Let me start with ternary representation of 1 by 4. Ternary representation of 1 by 4. So, I need to find its ternary representation, say 0.A1, A2, A3 and so on in base 3 using these 3 digits 0, 1 and 2. So, clearly 1 by 4 is less than 1 by 3. 1 by 4 is less than 1 by 3 because its denominator is more than 3. So, 1 by 4 will lie somewhere in this interval, and we will allot this 0 digit at first place. So, first place is obtained here for 1 by 4 after this point. The first for this fraction 1 by 4, if we are interested to write in ternary form. So, first digit will be 0. For the next digit, again we need to divide this sub interval 0 to 1 by 3 into 3 equal parts. So, let me draw here again this one, say this one is 0, this one is 1 by 3. Let me multiply it its numerator and denominator by 3, it will be 3 by 9. So, this point will be 1 by 9 and this will be 2 by 9. Now, again this 1 by 4 and 2 by 9, see if we cross multiply, then we have 9 here and 4 2s are 8 here. So, 9 is greater than 8 means this fraction is greater than 2 by 9. So, somewhere 1 by 4 will lie in this part, 1 by 4 will lie in this part. Again denote this by 1, 0, 1 and this interval by 2. So, since 1 by 4 lies in this part denoted by 2, so at next place we will allot the digit 2. Again choose this interval, divide into 3 equal parts. So, in this way the ternary representation of 1 by 4 is basically 0.20202 and so on in base 3. So, this one is the ternary representation of 1 by 4. Now, earlier what we have done, that in construction of Cantor set, since we have removed this open interval from 1 by 3 to 2 by 3. So, this that is denoted by 1. This means if any member is the member of Cantor set, then it will not be constituted using the digit 1. It will only involve zeros and 2s. So, since here this implies that 1 by 4 is member of the Cantor set denoted by F. Why it is member of the Cantor set F? Because it involves that only digits combination of 2 and 0, in other representation of Cantor set, this may be finite, this may be infinite. So, this is the way to identify whether a member is whether given any ternary representation of any real number. So, if it is not involving at any place the digit 1, so it will be a member of the Cantor set. So, I can write here another definition of Cantor set as a point x belonging to 0, 1, a member, a real number in 0, 1 is in the Cantor set F denoted by F, if and only if it can be written in base 3, that is ternary without the digit 1. So, 1 by 3, if we follow the similar procedure, so 1 by 3 has two representation. One is given by 0.1, 0, 0, 0 and so on in ternary form, and another as 0.01, 0 2 0 2 0 2. However, in my earlier lecture already I have discussed. Why? Because 1 by 3 is sharing the common boundary. Say this one is 0 1, and if on dividing into 3 equal parts, what will happen? This 1 by 3 is sharing the common boundary with this one, with the with this notation 0 and 1, I mean with the interval 0 to 1 by 3 and from 1 by 3 to 2 by 3. So, in ternary form we have both this representation, but since this representation it actually 1 by 3 has two alternate representation. Why? Because if we start from this one, 1 by 3 sharing to the boundary denoted by closed interval 0 to 1 by 3. So, at first place we have 0, and on dividing this 0 to 1 by 3, 0 to 1 by 3 again into 3 equal parts, I can write it as by 3 by 9. So, 1 by 9 and 2 by 9, again labeling this with 0, this by 1 and this by 2, and removing this mid one, because we are writing in Cantor form, or let us first write its ternary form. So, clearly this 1 by 3 is the last point, extreme point of the interval denoted by 2, box 2. So, again it is going to be in this place. So, the next digit is 2 here, next digit is 2 here. Okay, I have written it, let me correct it, this will be 0.222, 0.222 and so on. Why? Because again after selecting this interval and dividing into 3 equal parts, say 2 by 9 to this 3 by 9, 3 by 9, that is 1 by 3 will always be on the in the last box. If we divide it into 3 equal parts, then this is going to be the last part. This is the reason why all the digits will be 2 here. In next place all the digits will be 2. And if we start by choosing this point, say because it is also sharing 1 by 3 is common to the interval 1 by 3 to 2 by 3. So, at first place we have 1 here, and on taking this 1 by 3 to 2 by 3 and dividing again into 3 equal part denoted by 0, 1 and 2. So, 1 by 3 will each time will be the left extreme of this 0. This is the reason why all the digits after 1 will be 0. But out of this these two alternative representation, this one is since this one involves only 0 and 2 combination of 0 and 2. So, this one is the representation of Cantor set. However, this one is not the representation of Cantor set, because we have already removed at every step the middle third denoted by the symbol 1, and it involves the symbol 1. Due to this representation is not in Cantor's form, I mean not in the member of Cantor set. However, this one is allowed. Similarly, we have more examples here. Let us see some other examples to identify this one, whether it is a member of Cantor set or not. Similarly, 11 by 12 has Cantor representation as 0 point. One can try this 0.220, 220 and so on. I have taken this example, I will explain when we reach to the concept of fractal, that 1 by 4 has representation, 1 by 4 belongs to the Cantor set F, and if we translate it by 2 by 3, that is 11 by 12, then again this will have Cantor set representation. This will be member of the Cantor set. Why? Because it involves the digit using combination of 0 and 2 only. So, that is the method to identify a given number whether it is a member of the Cantor set or not. Some other example, let me take 1 by 2. 1 by 2 has representation as say 0.1111 and so on. So, clearly since it involves the digit 1, it is not member of the Cantor set, where F is the Cantor set. Other examples, say 2 by 3. 2 by 3, 0.2. Why? Just like in decimal system, if we recall in decimal system, suppose x is equal to 0.569 is given. How to obtain this 5? 5 by 10 plus, for this 6 we need to divide it again into 10 equal parts, and for this again into 10 equal parts. So, that will be 9 by 10 cube, but this is in the decimal form. So, similarly this is 0.2. Why? Because we are trying to write into the ternary form. So, at each step we need to divide into 3 equal parts. So, if I divide this 2 by 3, I will get 2 by 3. Next example is 8 by 9. 8 by 9 has this representation. So, again since it involves only the digits 2, that is from the combination of 0 to, so it is the member of the Cantor set. 8 by 9. Again 1 by 9, 1 by 9 is also the member of Cantor set. It has representation 0.002, 002 and so on. Again it is the combination of zeros and 2, so it belongs to the Cantor set. So, one can observe from here that after this this fraction may have finite representation or may have infinite representation. So, we have covered so far the construction of Cantor set. It's using ternary representation, that is sequence of from that after removing 1 we have the sequence of zeros and 2s to check whether a member is, whether any real number in 0 1 is member of Cantor set or not. Now, next part we will look at the some properties, that whether the Cantor set is closed or not, why it is uncountable. We will verify that length of Cantor set is 0, and after removing each open middle third, and sum of all those removed interval adds up to 1, and then these properties, and at the end I will discuss the idea of fractal, why Cantor set is one of the famous example of the self similar repeated structure which is invariant under transformation, some transformation, and is a very well known example of fractal. So, let us move to the next topic. Union 8 by 9 to 1. So, let us put here k equal to 0. So, we will get the first interval 0 by 3 square to 1 by 3 square, and in this way we have 4 intervals each of length 1 by 9, 4 intervals each of length 1 by 9. So, the Cantor set F is the intersection of the sets Fn obtained by successive removal of the open middle third starting with 0 1. Since it is the intersection of closed sets F, and we know that, see, arbitrary union of open set is open. Take its complement using De Morgan's law. We have finite arbitrary intersection of closed set. Arbitrary intersection of closed set is closed because each Cantor set is closed. Each of the F1, F2, Fi, Fn's are closed, and arbitrary intersection of closed set is closed. So, from there Cantor set is closed. F is itself and also Cantor set F is contained into each Fn. Why? Because Cantor set F is basically intersection of Fn from n equal to 1 to infinity. So, it has to be contained into each Fn for every n belonging to n. And also Cantor set is subset of the closed interval 0 1. In fact, this one is also subset of one of the subset of real number n is equal to 1 to infinity. So, using it, let us compute. See, the claim is that the total length of the removed interval is 1. We note that the first middle third has length 1 by 3 because we have removed the intervals from 1 by 3 to 2 by 3, and the length of this in 2 by 3 minus 1 by 3 is 1 by 3. In next part, we have removed 2 middle thirds of length 2 by 3 square of length 1 by 9. Just look at it. the length of this interval is 2 by 3 minus 1 by 3 1 by 3. Here we have removed two such intervals, the length of each of them is 2 by 9 minus 1 by 9, that is 1 by 9. So, if we add the length of all removed intervals, it will form a geometric series, say 1 by 3 by removing the first open middle third, two equal intervals each of length 1 by 9 and so on. So, this will form geometric series after taking 1 by 3 common here. If we take 1 by 3 common here, so it will be 1 plus 2 by 3 plus 2 by 3 whole square and so on. Now, this one is geometric series with common ratio less than 1. So, its sum of the n terms, sum of infinite terms is a upon 1 minus r, where r is the common ratio. So, if we apply this, then length of interval will be 1 by 3 into 1 upon, first term is 1 here, and 1 upon 1 minus 2 by 3. So, that is 1 by 3 into 1 upon 1 by 3. So, it will cancel out and length comes up to be 1. So, length of removed interval, sum of total length of the removed intervals is 1 here. Basically, F1 is 0 to 1 by 3 union 2 by 3 to 1. So, if we observe here F1, the length of F1 is, we have two intervals, each of the length 1 by 3. So, its length is 2 by 3. Here length is 1 by 3, length is 1 by 3. So, if we add these two lengths, we have 2 into 1 by 3. So, at up to nth stage, there will be total 2 to the power n. For F1 here we have 1 here. So, up to nth stage, we have total 2 to the power n pieces, each of length 1 by 3 to the power n. So, total length will be 2 to the power n into 1 by 3 to the power n, that is 2 by 3 to the power n. So, length of Cantor set up to Fn is 2 by 3 to the power n, but Cantor set C is formed by intersection of all such Fn for n equal to 1 to infinity. This means length is tending to 0. So, as n tends to infinity, this length of Cantor set is tending to 0, and since Cantor set is subset of all F1, F2, Fn, for all n in n, we see that if f can be said to have length, it must have length 0. Now, this property number 2 is very important. Why? Because the claim is that the Cantor set F contains no non-empty open intervals as a subset. So, if you recall the nested interval property, so indeed if F contains a non-empty open interval, suppose it contains a non-empty open interval, say open interval AB, its non-empty means A is not equal to B, then since if these Fn's, because Cantor set is formed by intersection of these Fn's, and if any interval, such interval AB is contained into C, then it has to be in all Fn, it has to be in all such Fn for all n in n, and its length is tending to 0. So, length of interval has to be less than equal to the length of the Cantor set, and this term is tending to 0. This implies from Archimedean property of R or from Sandwich theorem, we will claim that the length has to B minus A has to be 0, and if B is equal to, for this B will be equal to A, and A is basically your empty set, and we have started from the non-empty. We have taken in our assumption the non-empty, whether it is we have assumed that it is going to contain a non-empty open interval. So, this is not possible, and this is the reason why interior of F closure is equal to phi. How to find interior of any set? If we recall, see, F is a closed set, Cantor set is closed, being intersection of arbitrary intersection of closed set. So, F closure is equal to F closure of a closed set is same. Now, interior of F is actually the definition of interior of F is collection of all interior points, collection of all interior points, collection of all interior points of F, interior points of the Cantor set. So, suppose let us recall the definition of interior point. When we say that x belonging to F is an interior point, if around this x I can construct an open interval AB which contains this x and which is contained into the Cantor set. So, those points will be basically interior points of Cantor set. We are interested in finding the members of the Cantor set which are interior point, and for this I need to have at least one open interval AB which contains x and which is contained into F, and right now we have proved that Cantor set will never contain a non-empty open interval. So, this means that we will never have such open interval, a non-empty open interval containing x and which is contained into x. This is not possible. So, there is no interior point. Hence, interior of F closure is equal to phi, and this is actually definition of nowhere dense set. Nowhere dense set. So, Cantor set is nowhere dense. Now, next property. Also, Cantor set is compact. That we will have directly by Cantor set is compact. For this, recall the statement of Hein-Borel theorem, that closed and bounded subset is compact and Cantor set F is subset of 0, 1. This has upper bound as well as lower bound. Every real number greater than equal to 1 is its upper bound, and every real number less than equal to 0 is lower bound for this Cantor set. This means this set is bounded above. Cantor set is bounded. Cantor set is bounded and closed. Earlier we have proved that it is also closed. So, as per Hein-Borel statement, this is going to be compact. Cantor set is compact. Now, one more point I would like to recall here. If we observe F1, then 2 points, these boundary points 1 by 3 and 2 by 3 are there, and in next division into 3 equal part, the boundary points 1 by 3 and 2 by 3 are already there, and in between 0 to 1 by 3, 2 new points 1 by 9 and 2 by 9s are created. Similarly, 2 by 3 is here, and in between 2 by 3 to 1, 2 new points 7 by 9, 8 by 9 is created, and if we take intersection of all these F1, F2, so these boundary points will be retained. So, question is, can one name any other member of Cantor set which is not the boundary point? So, I have already given one of the example of the Cantor set which is not a boundary point, because if it is extreme point, then either after 0 all the terms will be 2, or after 2 all the terms will be 0. If it is in right extreme point, digit 2 will be allotted, and if it is in left extreme point of a boundary point, then on division we will allot 0 to it in Cantor set representation. So, 1 by 4 is a member of the Cantor set. 1 by 4 is a member of the Cantor set which is not a boundary point, not an end point of the interval of any interval. Now, next 2 points are remaining. This claim that the Cantor set contains all of the end points of the removed open intervals, and these are all points of the form 2 to the power k by 3 to the power n. There are infinitely many points of this form. See, n is varying with set of natural number. but apart from this there are other numbers also like 1 by 4 and so on. So we need to claim that this is basically uncountable, because countable union of countable set is countable. So I cannot conclude from here anything. Obviously there are infinite members. Now within infinite, whether it is countable or uncountable, so that will that is our next part. So the claim is that F is an uncountable set. Actually what I want to write here, interpret here, this 1 by 4 can be written as 0.20202 and so on. Now if we divide this by 2, it will be 0.10101 and so on in binary form. So all the members of Cantor set can be identified similar to members of closed interval 0 1, real numbers of closed interval 0 1, using the representation 0 and 1 in binary form. In ternary form we have removed 1. In binary form we are identifying the sequences of zeros to collection of sequences of zeros and 2s with there exists a similar, basically this the collection of all such sequences, collection of all sequences of zeros and 2s are similar to collection of all sequences of 0 and 1, because we know that every real number in closed interval 0 1 is uncountable, and that can be represented into binary form using the digits 0 and 1. So this will give an idea of developing of constructing a map which will map every member of the Cantor set, which will identify every member of the Cantor set to some members of in binary representation. So that is what written here, that if x belongs to 0 1, and we know that in ternary form if x is of the digit say form 0.a1, a2, a3 and so on in ternary form. So the first digit is obtained when we divide a1 by 3, next digit is obtained when we divide a2 further into 3 equal parts, 3 square and so on. So in every real number in ternary form of the closed interval 0 1 has this series representation, where an is either 0, 1 or 2, because we are talking so far of ternary representation. And since in construction of Cantor set we have seen that we are removing the open intervals 1 by 3 to 2 by 3 say at first step, this means digit 1 will not be involved, all those sequences we have to remove, and this is the reason why we can identify a member of any member of closed interval 0 1 if we divide of the Cantor set, we can project it. See here an is 0 or 2, this means this is the actually we are defining a member from F Cantor set to, we are defining a map from Cantor set to the real numbers in 0 1, real numbers in 0 1, and this one is uncountable, and we know that every real number in 0 1 can be represented in binary form, basically every this is the collection of all real numbers using the digit 0 and 1, and that one is uncountable. So we are taking an arbitrary member of x belonging to 0 1, and if we remove the all those sequences which contains at any stage the digit 1, so that is our Cantor set, that will become the member of the Cantor set. So what we are doing from this example, that we are dividing by 2. So if we divide at each place by 2, then all those will become member of the binary system. So this is the construction here, that if we take Bn is equal to An by 2, the digits of Cantor set we are dividing by 2. So it will be basically we are projecting the members of Cantor set with this map to the binary system Bn equal to An by 2, and clearly this map is surjective. Why surjective? Because corresponding to each Bn, here this one is Bn, I have An, because Bn and A are related. So in this way, since this one is one can identify the sequences of 0 to with the sequences of 0 1, and since sequences of 0 1 is of two distinct symbol is uncountable, hence Cantor set is uncountable. Or one can choose this map given here and use this composition map as discussed here to show that the Cantor set is uncountable. Cantor set is uncountable. So that's what. This idea comes from this one. This idea comes from this construction. That is phi of point A1, A2, A3 in base 3. When we divide by 2, it will be can be identified with 1-to-1 correspondence with the members of the binary system, and since this is uncountable, it has to be uncountable. Now the last part is observation of Cantor set as fractals. Cantor set is a very good example of self-similar repeated structure. Next is every point of Cantor set. I am giving you an idea how to think geometrically, that every point of Cantor set F is its limit point, Actually, if we observe the construction of Cantor set, then we have divided into 3 equal parts, remove the middle one, and this one is the structure remain. Again, at next step, we have divided into 3 equal parts, remove the open middle interval, and we are doing this process infinite times. We keep doing this infinite times. Now one can observe that this whole structure is getting repeated. And this Cantor set is shrinking because we are taking intersection. Now, if we recall the limit point, the claim is that every point of F is the limit point of the Cantor set is limit point. So for every x belonging to this Cantor set, basically limit point means every neighborhood, every open set here is either interval or union of intervals. Every open interval, every open set will intersect means intersection is will intersect with Cantor set. This is the reason why every member of the Cantor set is limit point. What is the reason here? See, if any point of Cantor set is given, then I need to show that whatever neighborhood is given to us containing this x, it will intersect, its intersection is non-empty, AB or union of AB, because let me start with this interval because open intervals are open in R. So here the logic is that because Cantor set, the nature of Cantor set is shrinking here. So at any stage, whatever be the interval AB, and Cantor set is defined as intersection of all such Fn from n equal to 1 to infinity. So at some stage, these elements will be within. After some stage, these elements will be within this interval, and hence this intersection is non-empty. And I can do this for each x belonging to the Cantor set. Now outside Cantor set, say outside it, we cannot claim any point to be limit point. Why? Because if outside it I choose any point, say x, then x minus 1, this distance is greater than 0, I can clearly make a cut whose intersection with the Cantor set is empty. So the points outside closed the Cantor set may not be will not be the limit point of the Cantor set, but all those points of the F is, and these are the only limit points of the set. This is the reason why Cantor set is a perfect set. One more property, Cantor set is totally disconnected. Cantor set is totally disconnected, actually all those sets are said to be connected. Just I am giving this brief idea. In my topology lectures I have covered this one. A set is said to be connected if it has no proper subset which is both open as well as closed. Open as well as closed. So not connected means we have a separation. That is, not connected means there exists at least one proper subset which is open as well as closed. Totally disconnected means singletons are the only connected subsets. Singletons are the only connected subsets, and whenever we take two or more points, then it will form disconnection. Singletons are the only connected subsets. For example, in connected, R is connected because it has no proper subset which is open as well as closed. So I am not going to cover this portion, just I am recalling this one. In my topology lectures I have discussed with several examples how to check that what we mean by totally disconnected in a separate lecture. Just I am recalling these points. So Cantor set is totally disconnected means the only singleton sets are only connected subsets of Cantor set. Now last point, Cantor set as a fractal. Cantor set as a fractal. So recall F1. What is F1? F1 is basically 0 to 1 by 3 union 2 by 3 to 1. This one is F1, and F2, let me write, F2 is 0 to 1 by 9 union 2 by 9 to say 1 by 3 union 2 by 3 to 7 by 9 union 8 by 9 to 1, and F3 so on. So Cantor set is basically repeating its structure, the whole pattern. So can we write Cantor set into a recurrence relation? Let me denote F0. Let us denote F0 as closed interval 0 1. So how to obtain F1 from F0? Look at, if we shrink the length of interval 0 1 to 1 by 3, then I can write that F1 is basically scaling of this interval 0 1, scaling of F0. If we multiply 1 by 3 to each terms of F0, I will get F1, the first part of F1, not the whole F1, in fact the first part of F1. So that will be denoted by say 0 to 1 by 3, Now I want to obtain the next one. So what I will do, if we translate this 0 by 2 by 3, then I will get the first point. This means, and again its length, see its length is 1 minus 2 by 3 is 1 by 3. So I need to see this 2 by 3 to 1. This is obtained by scaling 2 by 3 by translating it with 2 by 3, this with this one 0 to 1 by 3, say 1 by 3, 2 by 3 to 1 by 3 of f1 obtained, 1 by 3 of 1 by 3 of f naught, yes, 1 by 3 of f naught. By scaling f naught by 1 by 3, we will get the closed interval 0 to 1 by 3, and translate it by 2 by 3, we will get this one. So, in general f1 I can write as 1 by 3 of f naught plus union 1 by 3 of f naught union, because we have union of two intervals. So, this will be union 2 by 3 plus 1 by 3 of f naught. So, in general I can write the recurrence relation as fn plus 1 is equal to 1 by 3 of fn, the previous one, union 2 by 3 plus 1 by 3 of fn. In this we have the recurrence relation to generate fractals, the recurrence relation to generate fractals. So, why Cantor set is an example of fractal? Because it is self similar to the whole copy, self similar. This piece is copy of this one, these two pieces are copy of this one, and so on. And one can obtain, see the next f2, because f1 involves two such intervals. So, if I put the value of f1, see f2 will be 1 by 3 of f1 union 2 by 3 plus 1 by 3 of f1. Now, substitute the value of f1 here. f1 consists of two intervals. So, from here we have two intervals, and from here we have two intervals. So, total in f2 we have 4 intervals. So, this is the recurrence relation for fractal. So, each part is scaled down copy of the whole, and another is that the Cantor set is invariant under scaling. See, we are doing scaling here, and invariant under scaling by 1 by 3 and translation by 2 by 3. So, this is one of the example. So, this is the reason why Cantor set is one of the example of fractal. Totally disconnected I have not discussed in detail, but one can refer my topology lecture, there I have discussed it in detail, since it is beyond the course of real analysis. So, I am not going to discuss it here. That one is the part of basically in topology lectures I have discussed.